My name is Sandoval, and I'm a PhD student in computation at MIT. And I am excited to be presenting this project that I believe represents a different way of doing digital mapping, and I call it painting with data. So I'm going to present the development of this mapping and modeling tool that proposes a different paradigm for user interaction. The tool provides users with a more intuitive and visually based method of understanding spatial data in order to tell a compelling story without the upfront cost of spending a long time learning it. This tool, you're manipulating a map first and foremost rather than interacting with a database. This geospatial web application utilizes voxels as an alternative to traditional two-dimensional geospatial modeling techniques. The tool also introduces a visual programming language which allows on-the-fly functional geospatial computing. So you don't have to learn how to code. You can code visually with building blocks. So this extends this representational analytical modeling capacities to actual computing. The research project starts by acknowledging the limitations of Gis software, specifically its graphical representation and user interaction. The discrete graphical representation of spatial layers in GIS software constrains the capacity of the user to visually construct holistic intuitions of the relationships between spatial layers of information. Voxels are a computer graphics technique. They enable the construction of spatial models that provide a three-dimensional data structure for interactive multi-dimensional spatial computing and visual representation. GIS spatial tools oftentimes use analytical techniques such as map algebra that when computed by current spatial applications, disconnect the visual representation from the information and functional computation. So first you compute, and then you obtain representation out of it. In this traditional approach, as I said, the modeler first manipulates all the data and then ultimately ends up with a visual representation or a map or whatever data layer that is. In the past, voxels have also been proposed as a graphical and data structure for data structure representation for 3D and 4D spatial datasets. And analytical functions have been developed to implement map algebra operations in 3D and 4D. However, there's still a gap between representing information and computing with it, where the existing interfaces treat both processes as discrete. And what we're trying to do is merge both processes together. We compute as we see. The research project initiated by proposing a series of guidelines for the development of urban mapping platforms that could better support the needs of planners and citizens. I'm also in a city planning department in addition to the computation group where I'm at. So I work with city planners in general. This research project proposes urban modeling processes as an iterative method closer to design. So you see, you experience, and you reflect. You iteratively transform the models on the fly, rather than apply a set of predefined generalizable functional models. The lack of data modeling and representational transparency constructs barriers between stakeholders, designers, and the general public. So urban mapping tools should contribute to the disappearance of power structures between stakeholders, urban modelers, designers, and the citizens they serve. So by lowering the barriers of entry to urban tools and models, it is possible to motivate civic engagement, allowing a collective open-ended urban computing methodology. Lastly, one other thing that we're trying to do with this tool is propose hybrid approaches to computing. Urban computing methods should allow for an easy combination and integration of the intuitions generated visually, and then its construction into formal computational models. In this way, the modeling process can be iterative, contextual. We see and we reflect and we transform the models on the fly. Painting with data is a software developed as an initial step towards a series of guidelines that I generated. It is a historical and theoretical study, and it's proposed as an alternative to current platforms of mapping and computing. To accomplish a seamless user interaction, a major focus of the software development was the construction of a fast and robust functions capable of dealing with large amounts of information in the most computationally efficient manner as possible. The application is built on the web, and we separate the client operations from the backend operations that are more computationally intensive. The whole application is built on Node with a spatial database, etc. It's all open source, can be accessible and contributed on GitHub, because we want people to get involved in the development of the application too. And it provides a full pipeline from inputting data to transforming data into the voxel data structure, to representing it and computing with it. So we can basically upload any shapefile, any raster data set, and in the future, CSV files too. All of this lives on the web, on whatever browser. All of this is translated into a PostGIS database, and then we do some backend computing to translate from shapefiles or whatever format into voxels. We store all the data sets in a single database. The spatial database also provides functions for projecting from any number of projections that the native data might have into a single spatial projection. As I said, we used PostGIS, and we developed a number of queries to go from spatial data sets into spatial voxels, or data voxels, as we call it. What happens then is that we select multiple layers and we compile them into a single voxel. So a single voxel is a 2D or 3D number of layers on top of each other that are within a bounding box. So we have to select the layers that we want to have in the same voxel. Once all the layers are reprojected into the same spatial projection, a field of voxels is created within the bounding box of these layers, and we basically sample the values and the values inside all of the shapefiles, and we also weight them according to a number of heuristics. And then once all the backend data is processed, we have a front-end application, which is all developed on React. And we are actually using WebGL to display all the geometries, all the voxel structures. Overall, the front end of the system has four main components. The data input interface that allows users to upload new layers of information. We have a voxel geometry library that provides geometric and data support for the voxel structure, and UI that combines HTML elements with additional widgets and WebGL elements. The voxels layers are sampled and stored in a JSON file that then is requested by the client. We also have a number of spatial functions. For example, we have a k-nearest neighbors algorithm that since all the voxels are coming from discrete geometries such as shapefiles or vectors, we allow people to kind of like blend or smooth the values through a k-nearest neighbors algorithm. So for a voxel, we can average the nearest neighbors around it. So this is kind of like how it works. It basically interpolates all the values of the cells adjacent to it and selects the key number of neighbors. All of this data is three-dimensional. The third dimension can be either temporal. It can also be spatial. And we also have a parametric blending function between different colors, so users can freely select among them. The blending function parametrically assigns a color based on the pixel values, and the color ranges are defined by the user. The same datasets can therefore yield different visual representations and help us arrive to different conclusions. we believe, or I think that the combinations among these colors and intensities construct a memorable representation that directs the user's attention to what they want to see. They can also modify the opacity values of every individual layer on the fly. And all of this can also act as rules. They can basically act as different hierarchies between different layers, and they can modify them individually with a visual programming language. As I said, they can modify the values for the whole model or for individual layers through this relationship graph or visual programming language. If you guys are not familiar with visual programming languages, for example, Scratch, it's a tool that is used to teach kids how to code. It's basically building blocks that are connected by edges. So that way you don't need to actually input textual commands. You're just dragging and dropping blocks and connecting them with edges. We also have this thing that we call the Parallel Data Explorer at the bottom part of the screen that allow you to query different data sets on the fly. And it's multi-dimensional too. So in the context of the application, every voxel on the screen that is added to the model represents a single dimension in the parallel coordinates model. And every dimension in the model is represented by an axis. A data point, or a voxel in this case, is represented as a polyline, where the intersection with every axis represents its value at that particular dimension. This is visually powerful, and it creates visual intuitions among multi-dimensional conditions. And this is coupled with an on-the-fly interaction with the voxel geometries, merging spatial with tabular information visually. They can query a subset of voxels or polylines, visually refining an area of interest. And all of this is happening in real time. Up to this point, the application has been primarily dealing with utilizing voxels and voxel structures as representation with a real-time user interaction. But the visual programming language that I mentioned earlier was created to allow users to couple the visualization mechanisms with functional computing. So it integrates the possibility of data-driven calculations, manipulating spatial numerical values of the voxels through mathematical functions, logical functions, which also derive in transformations of the current representations and also create new layers of information. This visual programming language allows for an iterative real-time transformation of the models themselves, and they are extensible by the users. So all of this being open source, the users can also create their own nodes and create their own functions and contribute to the larger community, hopefully. So, for example, we can create a map algebra pretty easily with the programming language. Doing, in addition, some logistic functions, establishing some formal logic, combining multiple layers into new ones, and adding layers of information on the fly. In addition to the conventional 2D map algebra operations, the application implements 3D and 4D map algebra functions. And different to traditional approaches, all of this is happening on the fly and as you go. So you're adding nodes, you're connecting them with edges, and boom, it creates a new layer of information on your screen. We've been running a number of workshops and presentations in academic institutions, MIT, other schools in the area, and we have been collecting user feedback and responding to this feedback. Ultimately, what we're hoping to do is to make the application and also data and mapping and modeling more accessible to everyone. A number of things that we think we contribute to is first proposing voxels to represent spatial data. We are trying to combine visual computing with functional computing iteratively and on the fly through an open source and online availability. hopefully motivating civic engagement in policymaking, making data and modeling more accessible to everyone. So we also presented an alternative way of computing with spatial data, and what we hope is a different way of mapping and computing with it. Thank you, and let me know if you guys have any questions about the tool or the work.